the observability analysis, the only thing that it's doing, it is asking, is there any change in the output of my system? Is there any change on the measurement? If there's a change on the state.
Humberto Ramos was a control mechatronic design professor at the Universidad Politécnica del Sur de Zacatecas. He obtained his Ph.D. in 2020 in aerospace engineering from the Texas A&M University, and then he joined as a postdoctoral researcher for the University of Florida, and then now as a research scientist, specifically with the Autonomous Vehicle Laboratory in the UF REEF facility, where he collaborates with the Air Force Research Laboratory on problems such as GPS denied navigation, guidance, navigation controls, extending common filter for practical applicability. I wanted to start on a broad note. For example, you've done robotics, you've done aerospace, autonomous vehicles. So when you're thinking about those systems, they're pretty related, right? Because you have sensors that are gathering information. You're trying to figure out where you are, trying to figure out what you're going to do next, trying to figure out what the environment is. So maybe in those themes, could you briefly describe when you have this, or when you're trying to design a system like that, what are the different autonomy areas that exist in your view, or how would you split them, and what are you interested in? That I kind of already gave it away already.
Yeah, in robotics, robotics and any other aerospace related area, you always find these three main fields, which are guidance, navigation, and controls. The guidance answers the question on what are we going to do now that we're at the current state, and navigation answers the question, where are we right now, and controls answers the question on how do we act, how do we move, what do we do in order to go to where we want to go, given that we know where we are. So every time you have a robotic systems or aerospace system, you're about to design an algorithm, you should be thinking that you need to know where you are, what do you want to do, and how you want to achieve it. Mm-hmm. And that also applies to the ground robots, or a drone, or a robotic arm, a satellite, or a spacecraft. So every time I'm going to design a system, I think of those three things.
And there's also, I would add also the perception side maybe on the more robotics, maybe in aerospace might not be that used depending on the application. If it's a rover, probably. If it's a spacecraft, maybe not that much. But yeah, so you're mostly focused on the navigation side.
Right.
You said navigation side is basically trying to figure out what the state, your current state is, mm-hmm. and that state can be anything.
Yeah.
So that normally is achieved with estimators. Mm-hmm. Would you say that, like in a broad sense, you would try to solve this navigation problem with some sort of estimator?
Yeah.
So what is an estimator, and why you would need an estimator?
So an estimator is a set of steps that include mathematical expressions to use information in order to produce a solution on, in this case, where you are, or how fast you're moving, or what's your temperature, or what's your overall state of the system. It can be any system. An estimator is needed because if you were to use a sensor in a system, say you have a camera, or say you have a distance sensor or a sonar, all of these sensors have noise. They're imperfect. And even if you have this distance sensor that I mentioned, and you're using it to know how far you are from an object, you cannot rely only on the sensor because it has imperfections, it has noise. It will report the true distance plus some noise, or the true distance will be contaminated with electrical noise or some imperfections because of they're intrinsic to the sensor. So you cannot only rely on the sensor. On the other hand, and this will connect to why we need estimators, but on the other hand, you could use mathematical models to guess how far that object is if you're talking about this distance sensor. Or if you're using a camera, you can use a mathematical model to know where things are in space based on what you see on a camera. So you have a mathematical model for the camera, but similarly, these models are imperfect because a mathematical model at the end of the day is just a model. It's the best. It's the best you can do to describe reality. An equation is just an attempt to describe what's happening in the physical world. So because sensors are imperfect and mathematical models are imperfect, you cannot rely on only one of them. And an estimator provides the means to combine models and sensors information so that you can get a better idea of the phenomenon that you're observing, a better velocity estimate, a better position estimate, a better temperature estimate. In the case of satellites, a better pointing estimate. Because both parts, either model and sensors, they both have errors. So an estimator that provides this list of steps and math, they're aimed to help you fuse models and sensors information.
And briefly, on the noise and the disturbances you have on systems, because for example, when you have like a distance sensor, if you say we're 0.5 meters away from a wall or something like that, for example, I've been asked, it's like, okay, why don't you just take that as the truth, right? Like, why aren't you just 0.5 distance and that's it, right? Because not only you get noisy, as you were saying, for disturbances, it's kind of impossible to get the exact, like, right, the exact distance, because you're not 0.5, you're 0.5, 1, 2, 3, 7, 7, 5 meters, right? Or until when do you stop counting? And also in the model, like maybe a way of describing the errors in the model that people hopefully are familiar with is like something flying that you take air resistance as non-existent, right? If you have like some sort of projectile, that's maybe a way of saying that you kind of know what the object's gonna move if you assume some things are non-existent, or if you assume some things are simpler than what they are in real life. So for example, what are those types of assumptions, or what are the normal disturbances or noise that come into the problems that you are interested in airspace and robotics?
Yeah, so one source can be, so the sensors are just devices that measure changes in a generally in a smart way. So you might be sensing distance by contact, or maybe through sound, or maybe through vision, and it depends what kind of sensor you're using to measure that quantity. It will depend what sensor you use to determine what is affecting it. If you're using for example, you're using the airspeed, well, temperature of the air will affect that sensor, for example, because the speed of sound will vary based on that. So you need to compensate for that. If you're not compensating for temperature, that will affect your sensor. That's one source of noise or imperfection in your measurement. Another thing could be electrical noise. At the end of the day, you're using some sort of transducer to go from a physical quantity or pressure or force or some type of contact. You're changing that into a voltage or a current. So electric noise will affect that measurement as well. In the case of a camera, a disturbance can be, for example, lighting conditions. So it's not the same sensing or trying to find an object or trying to find a feature on the scene if there's low lighting conditions or if it's raining. That will affect your measurement on top of what the temperature might do on your sensor or the electrical noise on the sensor. So it depends on what sensor you're using. But there are many factors that can affect it. Other thing that we haven't talked about is something called bias. So you might have a systematic bias on your measurement because maybe you always place the sensor on the same platform, but the platform might not be, let's say you need a flat surface to mount your sensor. But if the surface is not flat or if it's inclined, you're always having that error in your measurement. So it's systematic. It's the way you're taking the measurement that is affecting. It's not the sensor itself, but the way you're using the sensor. That also might induce errors. And other sensors like an IMU, an inertial measurement unit, they're just not as stable by its nature. They might be affected by temperature, or they might be affected by large big shakes on it. That might affect something that is called accelerometer bias or gyroscopic bias. These quantities are not you cannot measure them directly. You cannot determine them directly off the box. So you need to do extra work to determine these errors first or online, and then correct your measurement. So again, it depends what sensor you're using. There are different sources of noise and errors. Yeah.
And how would you start solving these problems? Like when you're starting designing an estimator, what are the kinds of questions that you need to ask yourself in order to start solving this?
Sure. So there are different types of estimators.
Mm-hmm.
It can be you need to think about, is my system a linear system? Which there are non-linear systems in real life, but we pretend like if they were linear systems because it's convenient, it's easier than a non-linear system, which every single system is a non-linear system. So you need to think about linearity of the system. You need to think about
and a linear system, real quick, is kind of like a simpler model on the way that we express it mathematically, right? It's just like the way the math that you write the equations of that model. That linear model specifically is like a simpler way that when you start manipulating it, that manipulation becomes easier to deal with than nonlinear systems. Maybe that would be a way to put it.
I would say it's more general than that because there are some linear systems, nonlinear systems that are easy to manipulate as well.
Mm-hmm.
I would say more generally that a linear system is a system where you can apply superposition, and because the linear system might be difficult to handle if it's big, if it's complicated itself. Maybe there's an integral in the process. Maybe the differential equation it might be linear, but it might not be easy looking. But still, it will have a known solution most of the time because it is a linear system. And as you were saying, it's accurate to say that it's simpler to manipulate and solve. But there are also simple nonlinear systems. So I would just stick to the
technical definition
yeah,
of superposition, like
superposition.
And
Yes, that means it depends what kind of system it is.
Yeah.
If it is a mechanical system, if I apply the force 1 and 2 separately, I'll have the same result that if I apply the first force and then the second force. Or if an electrical system, if it's linear, we will have the same answer. We apply voltage 1 and 2 at the same time that if I apply them separately, the current will be the same on a resistor per se, but it needs to be a linear system. So that's following the definition. Yeah, and so that's one part of what to think about when you're designing an estimator. Another thing is what sensors you have available. So something very interesting about an estimator is that, well, the math, and we were talking about there are several types of estimators as well. We can also go into that. But one very interesting thing is that you can know in advance if with the system you have and the sensors you have, it is possible to have estimates of your state, even without implementing the system. Only with the model, the mathematical model of the sensor and the system itself, say a drone and it has a lidar or it has a camera. So only with this information you can determine if you're going to be able to estimate velocity using a camera, for example, for a given system. This is a concept called observability, right? So you can analyze that offline, even without having the system. And what that the reason that's very powerful is because on paper you can have a very good idea of what sensors you need or what are the properties you need, so that the math reveals that there's observability, meaning that you can estimate what you like to estimate. An example could be if I have a air sensor, if I'm sensing the speed of the air
in some aircraft, like that.
In some aircraft, or if I'm measuring pressure, for example. If I measure pressure, can I estimate my velocity? Or if I am measuring range to an object, if I want to track an object, say there's a satellite that you want to track, you can ask questions like, if I only know how far the satellite is, even if I don't know what the azimuth and elevation with respect to some radar on Earth is, if I only know range, can I know the speed of the satellite? If the observability analysis tells you yes, then you can do it. But on the other hand, you can just find no, it's not possible with this sensor to determine your velocity. You might determine other things like maybe position, or maybe some other quantities like the shape or inertia or other quantities, but maybe you cannot estimate certain quantities provided the measurements from this sensor. So that's very interesting there. In when you're designing an estimator, before implementing anything, you can just do an observability analysis and say what can I and cannot do.
Do you have an intuition on how the observability analysis or why it works?
Yeah. So sure, the observability analysis, the only thing that is doing, and we can get into mathematical, we can get into like more linear algebra stuff, but what it means physically is it is asking, is there any change in the output of my system? Is there any change on the measurement? If there's a change on the state. So if you are, so for example, if you're looking at, if you have a camera and you're trying to track an aircraft with this camera, you want to measure its displacement with the camera. But if you're assume this is a scenario where you have this camera perfectly aligned with the aircraft. At the center of the camera, you see the aircraft. At the center of the image, you can see the aircraft. And it turns out that is in this fictitious scenario, the aircraft is coming at you. It's coming at the camera directly. Well, if it's far enough, you see no change. Yeah. You see no change. The aircraft is moving, but you don't see it. You cannot, only from the measurements that you're getting, the center of the camera, you cannot determine a delta position, a change
The state is changing, but the measurement itself is not changing. Therefore, no information.
It's like there's no connection.
Mm-hmm.
Unless you tilt a little bit. If you tilt your camera a little bit, if you watch the aircraft from the side, a little bit from the side, you'll start to see some change. So the emotion starts to become observable. And if you write the math for that problem, and this is again a fictitious scenario, but you see in the mathematical expressions, you might see things like if the angle between my line of view for the camera, that center line, the optical axis, it's aligned with the aircraft, you will see something in the math like the cosine of this angle shouldn't be 90, it shouldn't be 0, because then my mathematical analysis breaks down in something like a singularity or some matrix cannot be invertible, and that translates into non-observable.
Gotcha.
So this kind of relationships. There's also, if you're tracking a falling body and you have a radar, you only have range, and you're observing this body falling vertically, and you keep track of it. At some point, your radar and the object will align in a horizontal line, and at that instant, even if the body changes its altitude, you won't see a change in your measurement. You will see no change in your angle. So it's not observable at that time. It's very similar to the airplane example. And there are other things. So in this case, you can have a more intuitive explanation of what the non-observability metric is. But there are other cases more that are a little bit more complicated. But still, everything boils down to: is there any connection between what I'm measuring and what I want to estimate?
Now, maybe this would be a good time to start it. Asking the question of what are Kalman filters, and maybe what are they useful, and if you can, a little bit of how or why do you think they work as well as they do?
Well, yeah, and we were talking about before. We were saying there are several types of estimators, and there are many research papers that might talk about a particle filter, a raw block-wallized particle filter, that might talk about a multi-Gaussian or Gaussian mixture filter. There are many things out there that you could use as an estimator. But yeah, the Kalman filter is the workhorse. It's the go-to every time. And if you have a project that involves estimating a state, I think you should definitely try it before going to a more exotic, to a more advanced filter. And the reason, or at least I see 3 reasons. One is it is robust enough to handle many cases, many systems. Another reason is it is simple to implement. It is very simple to implement. So you can just look at any book in the literature. You can look at any repo online. It's about 5 lines.
5 lines of code.
That's it.
Yeah.
It's very easy to implement. And the third reason I would say it is that it runs online. You can run it online. Many estimators out there might be very good for nonlinear systems. They're very good performance in the sense that they have minimum errors, when they are estimating the state of the system, but they might be very computationally heavy. And for real applications, you want to know where the aircraft is right now, not 2 seconds later. If you have a robotic system that is navigating your house, or you have a mower outside, you need to know where I am now, not.
And also, as you were saying, we have a certain capacity of computational resources, right? We cannot have a supercomputer in your mower, in your backyard. You only have like a certain limit of size of computer that can do a limit of computation.
Yes. There are limits there. So you want an estimator that can be run online, that is effective, and that you know how it works, or at least how to fix it if it doesn't work. Um, I think these are the main reasons why we still like the Kalman filter, and why there are still developments in my own work. It's about how to extend its applicability. Um, of course, it is not bulletproof. It will fail at some point if your system is um, non-linear enough, or if you have large uncertainty in your initial conditions. That meaning that you don't really know what are the initial values for your state. Mm-hmm. So that might break the filter. And there are some solutions out there as well that increase the capabilities of the Kalman filter, but that's our workhorse, and that's the one that you will always see in many papers, even before you test or try anything else.
Right, and for example, on the initial conditions, that you always need to have some initial guess, right? And our initial guess can be very good. Of like, I place my robot here, and I know exactly my robot is there, so I put in the computer. I'm fairly certain my robot is here. Or it can be that you just turn on the robot and in your house, and you have no idea where the robot in your house is, so you can just tell it, I could be anywhere in the house, so like any position, like in a very big area. That could also be a linear condition, but in that linear condition, probably the Kalman filter would fail, whereas in the first one, the Kalman filter would work. So do you have how does it work? Like, could you explain it in normal words of how would you start maybe deriving it, or why underneath the hood, like why are the things that you're doing in those 5 lines of code actually work?
Yeah, so this is actually one of my... I always say that the concepts are very simple, and sometimes the solutions to the concepts are maybe not that easy to understand. But the concept behind the Kalman filter it's actually very simple. The concept is you have a model, a mathematical model for your system, and I will use it to predict where the system is going to be in the next instant. And because I already know that it's going to be wrong, because we said our models are not perfect. So I know that. I know that if I use my differential equations or my mathematical model to predict where my system is going to be in the next instant, I know it is going to be wrong. So mathematically, what you do is you accept that error and say, okay, I know that my estimate of the state is incorrect. So I'm going to do a plus some amount, which is my error, the error that I incurred because I used the mathematical model. So you essentially write my estimate that I got from my model plus some error. If I was able to know what the error is, then I could fix my estimate perfectly. Mm-hmm. And the intent of the Kalman filter is to estimate that error. So the Kalman filter, what it's trying to do is, okay, I know I'm going to be wrong. I know I need to add some correction. And you could really, if you didn't know the Kalman filter, you could just add some quantity. What quantity? Maybe what you feel, let's say. What you feel it's the right amount. Mm-hmm. You can just add it. You could do, maybe you can program it in your computer and do, I'm just going to assume that every time I do a prediction, my prediction is 10% off from what it should report. So I could just do plus 1% of my current state. You could do that. Mm-hmm. And that will somewhat fix the error that you have. The advantage with the Kalman filter is that the Kalman filter will select that percentage of error for you. How? Well, mathematically what it does is that it will correct in a way that the covariance of your error, or the covariance of how much you're wrong, how much you're off, is minimized. So it is trying to select that correction in a way that every time that you apply it, the uncertainty on your belief, the uncertainty on your state decreases.
Yeah,
that's what it does.
Because it could also be worth noting that as you were mentioning, you don't not only have a state of like I'm thinking I'm going at 5 miles per hour, but you also have some sort of understanding of how confident you are about that state, right?
Yeah.
And that's where your covariance would come in. It's like I am, in a way, you could say I'm plus minus 0.1 meters per second kind of
right.
thing.
Yes. The Kalman filter, yes, exactly. On top of correcting your state, the Kalman filter, it gives you an estimated covariance or an estimated uncertainty on that estimate. So it will report these ranges for you. It will tell you, well, the velocity of the aircraft is, so many miles per hour, plus minus so much error. So it will give you these bounds on how wrong you might be. And in other words, the Kalman filter is telling you within this range, the actual value of the state should be
within this. And what you were saying that is important is that it's trying to minimize that uncertainty, right?
Correct.
If it was saying it's plus minus 0.1 meters, after doing this Kalman filter, it should be less than 0.1. It should be like 0.01 maybe.
Right. Or at least remain the same.
Or at least remain the same if you don't have any good information. So where does the measurements come in? And how do you incorporate this measurement? Because you've been talking about mostly about the state and errors, not the model, and errors between your model and the actual one. So like, how do you know what the actual state of your system is?
That's a very good question. And actually, that's a very good question. We don't know what the error is, because we don't know what the truth is, which is what we want to estimate in the first place. We don't know what the error is, again, because we don't know what the truth is. So we don't know how far we are. But what we do is we impose a model on the error. So what we do is, I know I'm going to be wrong every time. And that error, I'm just going to say that it is a random draw from a normal distribution. That's what we do. So we expect that the error is within some range. Mm-hmm. We don't know what the error is, but we could say that my error should be within these limits. Mm-hmm. That's something reasonable to do. And this translates into, well, the Kalman filter wants to estimate that error, and it also wants to give you an estimate of how wrong that error is. And the reason is we do it that way because, again, we don't know the truth. But we can impose a model on the error. And the error model is a Gaussian distribution on this error. So we impose that because we don't know anything else.
And the Gaussian would be like the normal bell curve.
The one that you see in high school, maybe in middle school, yes. That one you count the ages of the kids, and you count how many people there are, and you order the ages, you do the mean, you do the standard deviation, you draw that.
Yeah, do the mean. Like how or like if you stack the people's height, and you would expect there's little people that are very, very short, little people that are very, very tall, and then a lot of people that are
in kind of in the middle, what we call the mean, right?
The mean, right?
And yes, so we can assume, that's what we do in the Kalman filter. We assume that the errors that I will incur because of my wrong models will be distributed, or can be represented, or they will behave as if they were taken from a random draw from a normal distribution. So that's what we pretend. In reality, that's not always true. Yeah, there are, in many cases, you will see the errors behave like that. Very, very close. So the Kalman filter works very well. There are other cases where you might even have bimodal distributions, which means it seems that the system have two means. It looks like two Gaussian. I don't want to say two means, but two Gaussian distributions.
Like two bumps.
Two bumps, because the estimator might think that you were talking about position. Say one of those Roombas that clean your room, right? Your house. They're the vacuum cleaners. If they are using another type of filters or Kalman based filters, there are some instances where they might think they're in two places at the same time, but it's not because they are in two places at the same time. It's because based on what they measure and based on
the data
the model
from their sensors,
there are two possible solutions.
Mm-hmm.
Yeah. So
yeah, maybe a way is like if you open your eyes and this wall looks kind of the same as this wall, then you could be either here or here if
right.
you're like some distance away from them.
And this can like easily happen if you're only measuring distance to an object. Well, if you measure around and there are two places or three places that have the same distance, well, that there are different solutions, right? If you only have a radius as your measurement, well, you can be anywhere in that circle until you get more information to solve this ambiguity, right? So yeah, so in those cases, you might have a little bit more complicated distributions, but in the case of the Kalman filter, like the simple Kalman filter, the standard Kalman filter per se, it's one distribution for the errors, and that's what we do. We assume that the errors will behave like that, and yeah, it's very functional.
So lastly, maybe to finish, like what is the, or why are you interested in its applicability? Like when does it fail, and what are you trying to investigate of in practice? How do we make these failures less occurrent?
Yes, so this has to do with the three things that we primarily like about the Kalman filter. We like that it's simple, robust for many cases, and it runs on the line. However, if the system is very nonlinear, the Kalman filter it struggles to do a good job. Or if you have high uncertainty to start running your filter, that will also can break the filter very easily. And what I'm interested in is to answer the question, how do we get the most out of the Kalman filter? In other words, can we modify it just a little bit? Because I want to keep it simple. And I want to keep it small enough. The code needs to be, you can run it online. So if you can keep it simple and the code doesn't get complicated so that it's still running online, if I can modify the filter to handle more nonlinearity, a higher degree of uncertainty, that will be a win for the community because it's very likely that they already have a Kalman filter running and they're trying a Kalman filter. If you give them another option, an extension that is simple to implement, that is just a small modification of what they're already using, and that everyone is familiar with the Kalman filter. So if you give them these modifications that is still run online and are simple to implement, they will use it. So this will impact the community, and all the applications that use the Kalman filter, they will likely use these modifications to give a higher robustness to.
There's like tricks that you add on top of the same filter that you're doing. The same 5 lines of code, you just add maybe a sixth one that adds a little trick that makes the thing perform way better to whatever you're doing.
Yes, and we have some publications that talk about these modifications. We've shown a concept that is called the partial update. We have shown that this concept can work in any formulation of the Kalman filter. So far, we've implemented this in hardware, and we've seen that it definitely extends the envelope of systems that where you can use or where you can apply the Kalman filter. And now there are different labs that are using it, and we even have like public or open access repos that show how to use it.
And that's just something, right? Because at the end, like, you're just not doing it for yourself. You're doing it publicly and putting the code publicly so that people can benefit from what you're working. That's kind of like the point of research.
Yeah, and that's why we want to. That's the reason we want to extend the applicability, because it works for many systems, but if it can work for those systems where you would like to use it, but it's just limited at that for that specific case, that in many situations you're just you need to change, you need to transition into a particle filter or a unscented Kalman filter, which is a variation of the Kalman filter, or you need to go to Gaussian mixture. You need to go more advanced for your case in many cases. And maybe if you ask researchers, would you rather do a Kalman filter in this problem? I think they will tell you yes, because it is simpler, right? And if something is going on, or if there's a bug, the chances are I can find it easily. Or they might tell you, well, we've been trying this other filter which is more advanced, but it's complicated to implement, and we're not sure about some implementation details. Sometimes the literature, they have very nice results, new filters, very nice tracking, very nice estimates,
but it's hard to replicate.
And I think that's in any other subject as well.
Harder application in software, or it can be harder application in the math. Or how do you derive whatever the filter is to your specific application. Mm-hmm. Or they're doing tricks that you're not aware of.
They might have some tuning parameters that they got it right perfectly, for their system, but then when you want to use it for your system, it's a little bit tricky. And again, if you have that Kalman filter you already used in your classes, and you already have it, and you can validate it easily. If you add 2 lines of code and it increases its capabilities, I think people will tend to use that filter, and that's what we're looking for. Yeah.
Awesome. Well, thank you. You can find Humberto's research work if you Google Humberto's, and you should also check out Humberto's YouTube channel, where he's starting to explain more of these concepts for like everyday people, like coordinate transformations, and try to boil them down in a very simple, digestible manner, so you can then apply them in your research or just understand them for your own knowledge. So thank you, Humberto.
Yeah, thank you.
Yeah, we'll talk again.
All right. Sensors are imperfect, and mathematical models are imperfect. You cannot rely on only one of them. And an estimator provides the means to combine models and sensors information so that you can get a better idea of the phenomenon that you're observing.